Hello again. Last time we met, we built a rotor for our generator. This is our rotor. And today we need to make some coils. And coil making can be a long process. Takes a little bit of getting used to, and it takes some equipment which you can fabricate or pretty much adapt your variable speed drill to do the work for you. So we're going to need to come up with a set of coils, and I have plenty of coils here. We've been doing this for a long time. This happens to be one particular one we're going to work on today. You know, the coils can be various shapes and sizes. Basically, okay, and so you need a spool of wire to make coils from. This is a roll of 28 gauge that I just bought, 1 pound, and this is the size wire we usually use, something between 22 and 26 gauge. Okay, it's solid copper magnetic wire. Make sure it's solid copper magnetic wire. About 1,200 feet on this spool. Okay, and there are tables out there that will tell you how much wire you can put on one of these coils. It's just a little bit of math to do, and I have some worksheets that I developed on that you might want to review. Okay. What other things will you need? You probably need some tape. This is a narrow tape, so here's a coil that you can see how we fastened it when we were done. Okay, so every coil has a certain thickness to it. It has a certain outer diameter and an inner diameter. Okay, the inner diameter, it's as a good rule of thumb, okay, the inner diameter should be about the width of your coil, your magnet, excuse me. So it's a little small. Okay, so this is probably a pretty good combination. Now, the way electricity is generated is the magnet moves over the coil, and when the magnet is moving at right angles to the coil, the maximum amount of voltage is generated. So this is the sweet spot right in here, this side little bit. Okay, and there needs to be a space between coils, okay, and magnets, so that the shape of the waveform can be completed. For the magnetic flux to flow to the next coil. Okay, and so it's a changing magnetic field cutting across perpendicular to these coils that generates the voltage. One rule that you've got to think about too is that the fact that the magnetic field decreases by the inverse of the square. Okay, so what does that mean for coil maker? And again, I have a box full of coils here, but a thick coil doesn't really help you a lot. So a coil, say for instance this coil, is much thicker than this coil. Okay, so if you can, you want to get your coils as flat as you can. Again, you want as much area to be perpendicular to the movement of the coil, okay, to the magnet across the coil. Okay, so all of that has to be considered, and you're going to need, usually we use 4 coils for 4 magnets, so you can change that up. Okay, and we won't talk too much about that, but we'll just stick with that as a general rule. So the magnets will go someplace in here. Okay, where? Well, that's one of the things we've got to figure out. And they'll be glued in, and the rotor will pass over them. So again, if you think about, put the rotor on the other side, you can see the magnet. There's a magnet in there. So that magnet is pretty much passing right over the coil. Okay. Okay, the busy work is making the coil. This is this machine here is a coil winder. Okay, they're bought online. They're pretty cheap, considering all that you get for your money. It's pretty cheap. They don't come with the wood base and all, so you'd have to make this kind of thing up. And if you're doing a lot of coil making, and you've been doing this project for a long time, you plan on doing it, it's a very good investment. Okay, so it has, nice thing about it is it has a counter, so it tells you how many coils you have. Okay, this particular one has a chuck. The newer ones won't come with a chuck. You can add a chuck, take it off an old drill, or find some other way of holding on. Then you need some kind of form. This is a form I made up, printed in 3D. It actually is the same form twice. Okay, so it has a triangle in the middle. Okay, I know it's hard to see this because it's black on black. There's a little triangle in the middle. It's got these slots. Okay, and so the slots, so what I use the slots for is a piece of wire goes in these slots. Let's find one. It's got some glue in it. So the wire will go in the slot across to the other slot that matches it. Okay, on the other side. So we wind the coil. We got 3 of these wires. When we're done, we take the coil off. That's this wire right here. Okay, so we use that to hold the coil together. Now this coil is pretty flat. It's going to want to curl up. So what we usually do is we'll put some super glue on it. Okay, or tape it. Okay, and so this is the final coil, and you're going to need 4 of these. If you don't have a machine, then you can use your variable speed drill, and we've made up other combinations of parts. This happens to be a bolt to cut the shaft off, and it becomes a coil winder. We wind the coils on here. These little spacers just give us the thickness of our coil. We have another side here. Not as sophisticated, but it works. During COVID, we actually did some outreach with students. They were building these at home. We made these little disposable coil winding jigs. Looks pretty similar. It's very simple. It's got a slot for 1 piece of wire. This was a smaller coil, and again, you could put this in a drill, or you could actually wind it by hand. Okay, depending on how many turns you need. Okay, so you make one, you count one very carefully, right? Takes you a while. Even when we were using the machine to make a good coil, it took us about probably 20 minutes to finish a good coil. I like the way the coils when I'm done, and you compare the weights, and you can find out the count. Now this happens, we happen to mark this one as 24, number 24 wire, 300 turns. Okay, so that's that thickness, and that will just about fit in here. Okay, now whether or not that's a good coil for this, it all comes to, let's go and look at it. Yeah. Okay, so there it is. Okay, so you may make a lot of mistakes in these days, and I saved the mistakes because we used the little pieces of wire to wrap up. We've used black tape on occasion. We've tried all kinds of different combinations, and we could tie them with string. Okay, so and then you can just take the whole thing if you're really good at it, but it's not an easy task. So again, so before you make 4 of these, test the one that you made and see if that really is what you need for this particular project. Okay. All right, now we're going to test that one coil we made to see if it really is the coil or the coils that we want to make another 3 of. Okay. So we got a generator here, well, future generator, not finished generator. We've got the rotor we made. We got our multimeter. Okay. And turn my multimeter on. Again, we'll be reading volts AC. Okay. So we're going to see how that one coil works. Okay, now, when you finish these coils, first thing you got to do is take the varnish off the end of them. This is a varnished wire. Okay, the wire has a very thin insulation on it, and in order to remove it, you can sand it off. Okay, and some wires will have a green varnish on it. It's easier to see, but most wires have this clear varnish, really hard to see, and so you can take it off this way. Okay. And get all the sides clean. You'll see that it's a little shinier when you're done. Now another method, if you're doing a lot of them, is use a little torch. You can heat it up, and the varnish just goes away instantly. Okay, then you have to clean the wires to take the any corrosion that's on it off. So first thing I would do after I finish doing that is I would make sure that my connections are good. And so if I use the ohms range, I connect up my meter, and I should see maybe some low resistance. And when I talk about lower, 3 ohms is a low resistance. Okay, should be something less than 100 ohms, much less, probably less than 10 ohms. Okay, so that's the resistance of one coil. The 4 coils in series will be 4 times that, about 12 ohms. Okay, so now I'm going to switch back to my voltage range. I'm going to make sure my meter is reading AC and not DC. This particular meter, you have to push a button. Okay, you can see that I lit it up. You should be able to see that. Okay, so what I'm going to do, I'm going to put my rotor in on the shaft here. I just happen to have this shaft. Has some residual glue from when we glued it, which I didn't clean. That's the reason why you don't keep the shaft in the hole when you're doing the gluing. Okay, so now I'm going to, can you see my rotor? I'm going to just tighten up my screws here. Now, we should see a couple of things here. I'm going to mount this in my drill. And I'm going to run this on the highest of the low speeds. Okay, I don't want it to throw in any magnets here, so I'm going to keep the speed to that about, remember we saw it was about 300 RPMs, 350 RPMs. That's a safe speed. Okay. There we are. Okay. Now, if I can juggle all this stuff at once, I have to change. Oh, I am on volts. So we should see some voltage being generated. Alright, so watch, see that? And you can see that the coil has a sweet spot where the magnets want to cross it. Now, that's just a preliminary test. The real test we should set up right now. So let's take this off again. Okay, so got an LED stuck in there. So this is the normal setup. No, it isn't the normal setup, excuse me. Normally, the magnets would be on this side, be over here, okay? Okay, so what we're doing now, I have a stopper here, can you see that? Stops against. And I'm going to put the stator against the plastic. Okay, I'm just going to hand tighten these. Not going to take much. Okay. All right, loosen up a little. Okay. So, if, say for instance, you had different teams making coils and you want to test the coils, let me see if I have a second coil here we can test. Here's a coil. So we got, let's say we have these two different coils. We have that coil, we have this coil. Okay, so the rule says that this coil, more wire, more copper, should generate more voltage than this coil. Less copper. Okay. So we call this the induced voltage. The induced voltage is affected by the number of turns of wire that magnets have to cut across. Okay, so in this case, there's fewer wires to be cut across. And look, they're pretty much the same thickness, so the distance from the rotor is not going to be an issue. Now, the second one, I didn't clean the wires yet, and it has a real brown color to it, so I'm going to clean those wires off. There we go. Okay. Now I will check when I put this in the circuit to see if I've actually cleaned those wires effectively. But here we are. Okay, so this is the test. I'm just going to hold the coil in here and move it around and see if now this way is not going to be a big issue. It's just a matter of coming in and out. And this particular coil really doesn't have much room to go. It's pretty much where it is. Okay, so I am on volts. AC. Okay, let me hook my drill up. think you notice that when I move, I don't know if you can see this, but as I move closer to the center, the voltage drops. When I come out this way, it's not a heck of a lot of distance. The other thing I'm going to do is give this coil a little turn. Let's try it. So I got up to 0.9 volts. There's my 0.9 volts. I move it in. There's my 0.8 volts. So this is the place I want to be as far as a 10. Now I'm going to give it a slow turn. And I found an 8 volt. So it goes a little lower there. Right there. That's the spot it wants to be. I can't really see the hole because I got tape over it, but the orientation, if we notice that the magnets are actually cutting straight across this part of the coil. Okay. Okay. So up to 9/10 of a volt, so 4 of those will give us 4 times that voltage at that RPMs. Okay. And now where is my brown coil? Here it is. Here's my little brown coil. And this is a better example of location because you notice I can move it in, I can move it out. Okay, so let's try this. First thing I'm going to do is, I should always do, is just check for continuity, make sure I have a circuit. So I'm going to switch back to the ohm range. 4 ohms. Remember the 3.94 ohms. Okay, a little higher resistance, smaller wire size will give you higher resistance. Okay, so this is actually a commercially made coil. The other one was a student-made coil. I'm going to switch back to AC. And again, we use one standard speed, full speed, low range, for our measurements, so we have a reference point. We don't want to have too many variables when we're measuring data. There we go. 0.5 volts, 0.6 volts, 0.6 volts, 0.4 volts. 6.5. Now I'm going to turn my coil. Okay, so again, there is a sweet spot. I got to get that again. There it is. So on this one, you can see now from the picture how the magnet is cutting across this side. Now, my challenge to you is this. Why isn't this side straight? Okay, so I think, and again, I don't have a coil here that we can test, but a coil which would have more of a pie shape. Okay, more of a pie shape. Okay, that comes back here, and again, encompasses that the hole in the magnet passes over the rotor. Now, this test, you could take this test here again and change out the rotor. Okay, so if you wanted to check different magnet configurations, again, keep something constant. For instance, this coil with a different set of magnets or a different magnet placement. Okay, so you go through all those different scenarios to find your best combination. Okay, so when you settle on a good combination, then the next step is to make the rotor. Did I say make a rotor? No, make a stator. Make another stator. Okay, so I have a couple of samples that have been made already, and I'm going to show you these. But I want you to notice that what we need to do here in the final outcome of this, after you've made your coils, okay, you've tested that one coil. Oh, that looks good. I'll make 4 coils. I came up with the perfect location for them. So now I've got to put them in here someplace. Okay, so again, if I had 4 of these, I'd have to place 4 of them at 90 degrees from each other, right? One of the big considerations, and it doesn't seem like it's a big issue, but it is a big issue, and that is when these machines are running, they vibrate, and wires, if there's any wire loose in here, like if this particular wire, and again the rotor would be out here, not behind the, okay, so the normal, whoops, I gotta be careful. The rotor was, this is where the rotor would be, okay, and the magnets in here. Okay, so we got to keep these wires from catching those moving magnets. That's not always possible if things are not glued well. I don't know if you can see this one, but this particular stator has many wires kind of frayed inside here because they got caught on the rotating rotor. I'll slide it back. I don't know if you can. I'll take this apart. Nice thing about this generator, this is it. Right here. That's it. Isn't that cool? Okay, if you look at it, be careful where you put your magnets. So here you see a stator that has been glued in. Okay, that's the sweet spot, and we see a lot of wire in here, and hopefully it's all glued down and free from shaking. I can see a couple of coils here that did get nicked at some time, and maybe the rotor was moving, or maybe the rotor came just too close to the coils and started to nab them. The nice thing about tape or wire, or excuse me, string, is that it holds everything tight. Super glue, sometimes you'll not catch all the wires. But this actually has a combination of super glue, tape, and then eventually we just take a glue gun, right, and glue everything right to the back plate. So then the next thing is you've got to run these wires in such a location as to get them so they don't get caught on the rotating rotor. Okay, so let me reassemble this generator. Again, this is really easy to do, and we know that the clearance has to be adjusted between the rotor and the stator, or else we may lose coils. Okay, I got this lock here on this side, a spacer lock, same thing. Okay. Now in this case, this clearance has to be measured. I'm not going to tighten it down because I don't have a tool here to measure the clearance, but this particular design has a little safety feature built into it, in that the magnets kind of sit behind this plastic, so if the machine is run at really high speeds, which they sometimes do get run at very high speeds, and the magnets throw, they're going to hopefully get caught by this. If not, you can always tape some cardboard around here if you're doing a lot of high-speed testing. Okay. Okay, so that one's going aside. That brings us to this one. This is the one we're working on. Okay, so again, disassemble. I use the plastic screws again because I can tighten them by hand and they don't strip out of the plastic. Usually you'll strip the kids will strip the heads off the screws before they strip the rotor. Okay. So this is, you can remove the stator to do this work. Or you could leave it in like this, and we've made so many different stators I can't keep track of which ones have holes in the back and which ones don't. But in this case, your wires could be run through the hole, and again, everything's got to be in such a place that it doesn't get caught up in the rotating rotor. Now, we know that these are going to be at 90 degrees from each other, all four of them. So we need to establish a polarity of these coils so that when the magnet goes by it, it generates a voltage in one direction, and when it passes the next one, it should generate the voltage in the opposite direction. Okay, so there's a set of rules for generators, okay, that tells us this, and we won't go into the technical aspects of it, but it's pretty simple to check and see if these in fact are working the way they should be, or placed properly in the way they should be placed. So here's a inexpensive magnet coil holder, excuse me, battery holder, and I'm using one D cell. I've had these for like 10 years now, and so if I connect, and so I need that, and I need a compass, okay, to check the polarity of the field. When this coil is energized, it becomes an electromagnet, okay, and so we can check to make sure that one's a north pole and one's a south pole. In case we only have two coils, usually we have four, so it'll be north south north south. Okay, but we're making it simple here. We're just having two coils, and this would actually generate electricity with just two coils. Now I'm using the D cell. I mean, you could buy the, this is a 9-volt, but you'll eat up a lot of these with the kids checking their coils, because they usually just leave them hooked up and forget to disconnect them. Okay, so I'm going to take this particular, I'm just going to take a coil here that I happen to have in one of these brown coils. See if I can take it down. All right, so there's that brown coil. I'm going to hook it up to my, I've stripped, I hope I've stripped the wires good enough. I could check with my meter. Okay, now you need to remember, there's a couple of things you have that is important here. This is going to be the top. Okay, this is going to be the negative lead, and that's going to be the positive lead. Okay, the other coil, when it's sitting like this, so this will be the top, this will be the negative. Let's change these around, because they want to go that way. Okay, so sometimes you see a little spark when you hook these up. Whoops, my other wire came off. There's not much resistance here, so the coils draw a lot of current. They'll actually get warm, and again, they'll burn up the battery very quickly if you keep it hooked up for a long time. So sometimes you can just hold this on here while you're doing the measurements. A lot of times I'll just use alligator clips. Okay, so there we are. Here's my compass. If I flip the whoops, I don't see a reading here. I don't see a, oh, whoops, it just popped off. I think we better go with the alligator clips. Those particular connectors are not working. Alligator clip. Okay, so, So when the coil is sitting this way with this hook up, this is the negative side of the coil. Now notice that a lot of times if I flip the coil, whoops, there it goes. Okay, so sometimes when I flip the coil over, you may have to move the magnet away because there's not a very strong magnetic field here. It's pretty weak. Okay, so that's going to be the, if this is hooked up with this lead being the positive lead, this lead being the negative lead, and this the top, that's going to be the polarity. Okay. And as you can see, all I got to do is flip the coil over to get the other polarity. Okay. So these, when we're finished with this, the two coils will be wired together. So I'll just do this on the bench right here. We'll click like. Okay, let's see if I can get this to work. Okay, so where the meter, where the battery is, will be the output of the generator. Okay, and when it's working as a generator, right now it's just working as an electromagnet. Okay, I think both coils are energized. Compass will let us know. Flip one of the coils over. Yes, it's working, right? So here, they're both south poles now, the way they're wired. So I flip this one over. It becomes the north pole. Again, not a very strong force. Oh, you can see that. I'll do it out here. There's the negative, excuse me, the north pole. Come on. I might have lost my connection here. Looks like a north pole. Flip it over. Looks like a south pole. Okay. My coil might be weak. My battery might be weak. That's definitely a south pole. It's definitely a north pole. Nope. See that? The lead was, and that is a north pole. So these would go, disconnect the battery. Disconnect the battery. So again, we got some excess wire and all the rest, but I don't want to change the polarity, so they would go in here like this. Right, one on either side. These leads would go through, and that would be the output of the generator. That one and this one. And again, you got to keep the wires from getting caught in the, right? You got to keep your wires from getting caught. Again, you already tested for the sweet spot, so make sure you have it, you know, wherever the sweet spot is for that coil, that's where you want to glue it. Again, sweet spot also is concerned about the way the magnet crosses the coil. Okay, and that perpendicular side. So you may actually have to rotate it a little bit. Okay. This is all critical in getting tensible volts. Not a heck of a lot of difference, but you know, for a real fine tuning, then you can be concerned about that. Okay. The other thing, and after everything is glued down, and make sure nothing can actually get caught up in the rotating elements. The other thing is to get the rotor as close as you can to the stator. You're finished the design portion, and so now you're ready to give your generator its final test. The clearance here, again, this clearance is really important. Okay, and your rotor should be pretty true. It may be out a little bit. Make sure that you, again, keep the magnets from hitting the coils, but get them as close as you can. Okay. You notice on the back side here we see all our wires. These are actually soldered together. You could use clip type connectors, especially for testing purposes. So here's my output leads, these two output leads. And if you look on the back of this, we've actually written a lot of information about the actual output of the generator, so we don't have to keep looking up the data on this particular machine. So it says here that it looks like the internal resistance is 20 ohms, and that we're able to get 5.4 volts, no load, at 360 RPMs. And at 30 ohms, we were able to get 3.4 volts, which came out when we did the calculation of 0.38 watts, which I think is pretty much standard for this particular generator. And that is a generator with, it's got a stacked pair of neo magnets in it, and I think it's 250 turn coils. Okay. It probably can do better than that with a little bit of modification. Okay. The advantage of this particular generator is it's non-clogging. It turns very freely when it's not loaded. It's easy to start up, and then when you load it down, it slows down and produces power. Okay, well that's making coils and building your stator. Stator, yes, correct. Thank you. Now, to see if your generator is working, you can just take an LED. This happens to be the LED, and it doesn't matter how you connect these leads up. Okay, so connect one lead to each side of your LED, and give it the hand spin by hand, and you see that it doesn't really take many volts to light the LED. Whoops, don't touch the lead. There we go. Okay, so about 1.8 volts to get the LED to light. And again, you can take your drill. And the blinking is because this is alternating current, and a diode only allows current to flow in one direction. Okay. Something you can do too is if you connect two diodes back to back, and there's a little notch on a diode tells you the negative side, or there's a shorter lead. So it's one of two things, either, or in this case it's both. It's got a short lead and it has a little notch. So I've taken and connected two LEDs back to back, and so if you want to talk about what this AC voltage is, this is kind of a good, whoops, it's a good example of it. Whoops, I lost my, wrong lead. Okay, so. And you can see them blinking side by side, right? And again, this test at the low speed of your particular drill is a good test. Okay, so here we're testing at 360 RPMs, right? because it says it on the drill. We can also check if you have an a DC generator. You can always so there's a low-cost tachometer that will measure the speed of the drill or your generator. And again, here there's a silver tape on this, and I believe it. Oops. Okay. And it's actually a little higher than the 360 or 375. It probably varies depending on the condition of the battery. Okay. So the second test, all right, again, second test is the load test. And we know the generator works. We saw the LEDs blinking. So students, if they don't understand the significance of that voltage reading, they know that this generator is doing something, and it's doing enough of that, whatever it is, to light the LEDs. This case is going to be working a lot harder with this 30 ohm resistor. And the test with the 30 ohm resistor, and again we'll use that 360 RPMs as standard. So we see about 3.1 volt here, and okay, so we're measuring 360 RPMs, 3.1 volt. And we can actually calculate the power, how many watts are we generating, and that is 3.1 squared divided by 30 ohms. So it's the voltage over voltage squared over the resistance will give us the wattage. Okay. So if you just do a quick brain thing, it's going to be like 9 over 30, right? And so that is going to be like let's see, what do we got? 30 into 9, about 0.3, okay, 0.3 watts. Okay? And even more useful is the fact that